We have talked about the definite integrals, and we said that definite integrals are actually linked to the net area and the curve. And we also talked about the fundamental theorem of calculus. Now, I want us to talk about indefinite integrals and take some examples and also look at some of the common indefinite integrals that you just have to know by heart, because usually in the exam you don't usually get these integration tables. You have to know them by heart. You don't have a choice. You just have to know them by heart. What are indefinite integrals? Indefinite integrals are very simple. It is just, in simple terms, the most general antiderivative of a function. That is what an indefinite integral is. Let me just write the definition here in notation. The most general antiderivative. So the most general antiderivative is called, the indefinite integral. So, which means we have been doing indefinite integrals when we're doing the most, or when we're trying to find the most general antiderivative, because it's one and the same thing, right? In general, let me start writing here. In general, if I'm having f of x dx, this one here is the used notation. It is the used notation for the indefinite integral of f. Simply put, this one here, writing this without the lower bound and the upper bound, we are actually saying find the most general antiderivative of this function. That is the meaning. But once you have the upper bound and the lower bound, we are actually telling you that find the particular antiderivative and evaluate at this point, and then subtract the evaluation at the lower bound, not bound, the lower limit of integration. So that is the difference between those two things. Excuse me. So that is, what do I want to write here? That is this elongated s of f of x dx is the same as just the most general antiderivative of x, which such that if I take the derivative with respect to x of this, I am going to get this function here, which is f of x. That is the simplest at its best. Indefinite integrals, it simply means the most general antiderivative of a given function, and it is denoted by this. So when you are seeing this indefinite integral, you must know that I want you to find the most general antiderivative. And then here we have what I call integration. We have integration. We have this integration table, or simply put, some of the properties of this integral. So basic integrations, if I may put it like that. So if you want to find the the indefinite, this is not the good writing thing because it's not specific enough. Let me write table of indefinite integrals. think now we're specific enough. So if we wanted to find the most general antiderivative of the sum of two functions, or just the indefinite integral, you can just find the most general antiderivative of f of x with respect to x, and then find the most general antiderivative of g of x with respect to x and add them up. That's how easy this thing is. The second one is saying, if you are having two functions f of x being subtracted together, and you have your d of x, you can always actually find the indefinite integral of the first function and subtract the indefinite integral of the second function, and then you will be sorted. Let's go to number 3. And then if, let's say, you want to find the indefinite integral of a constant times a function, all you need to do, you can pull the constant out and find the indefinite integral of that function with respect to x. Let's go to number 4. And then now, if you want to find the indefinite integral of x raised to n dx, all you need to do here, just add a 1 there, n plus 1, and then you divide by n plus 1. Of course, you will have a nice plus c at the end, whereby this is a constant of integration, given that your n is not equal to 1, because if n is equal to 1, you know that the most general antiderivative of 1 over x is a ln function. So that is what is happening. The most the most general antiderivative of this, we know it is that. And then the fifth one is, if I take 1 over x and I want to find the most general antiderivative of that, is supposed to be ln of the absolute value of x plus a c. We are using the absolute value of x so that we can also talk about the case whereby x is negative, because a ln function can always take only the positive values of x. And then the sixth one is saying the most general antiderivative of e to the power x with respect to x is just gonna be the same as e to the power x plus the constant of integration. But if we are looking for the most general antiderivative of e time raised to an exponent k times x with respect to x, we are going to end up having to divide 1 by k, and you have an e raised to kx not dx plus the constant of integration. The eighth one is saying, if you want to find the most general antiderivative of a raised to x and then dx, you must know for sure that this is the same as a raised to x divided by the natural log of the constant a plus the constant of integration. Of course, if you are good with this and you understand this, you can actually prove this using this one over there. And then the ninth one is going to be if, let's say, let me write a 9 there, I want the most general antiderivative of sine of x with respect to x, I must know for sure that I'm going to get a minus cosine of x plus the constant of integration c. And then the 10th one is saying that the most general antiderivative of cosine of x with respect to x is simply going to be, because what is the function such that when I'm taking its derivative I get a cosine, I know that is supposed to be just a sine of x plus the constant of integration. In other words, if I take the derivative of this, I should get that. If I take the derivative of that, I should get that. But if I want the antiderivative, I should get that. It's the vice versa. And then let's look at number 11. If I want the most general antiderivative of sec squared x with respect to x, I am supposed to get tan of x plus some c. And if I am looking number 12, almost there, if I want to find the most general antiderivative of cosecant squared x with respect to x is supposed to be the same as minus cot of x plus the constant of integration. And the 13th one is saying, if I want the most general antiderivative of sec of x times tan of x dx, I'm supposed to get the same thing as just a sec of x plus a constant of integration c. And then let's go to the 14th one, the most general antiderivative of cosecant x, and then multiply by cot of x with respect to x is the same as minus cosecant x, and then plus the constant of integration. And the last one, if I want to find the most general antiderivative of 1 divided by x squared plus 1 with respect to x, I must know that it is the same as the inverse tan of x plus the constant of integration. Once you know these things, trust me, you already know integration as a whole, and you also already know definite and indefinite integrals. If you can keep these in your mind, it's only 15 things, just these 15 things, and then you should be able to solve as many problems given that you know these things. Let's take some examples and see how far can we go when it comes to the indefinite integrals. So this is the example that I have for you, and of course if we can deal with these examples, I think we actually gonna be ready to move forward. Let's say I have the first example. Let me just say this first. Find the general okay, this is one way. Someone might say find the most general antiderivative of each of the following functions. So you can find this question. This question is equivalent to evaluate functions f. Evaluate each of the following indefinite integrals. Okay, we can either someone say calculate, evaluate the value. All these things, they mean the same thing. All you need to know is the how to. The first one is saying I want you to find the indefinite integral, or the most general antiderivative of 10 times x to the power 4 minus 2 sec squared x, and then you have your dx. That's the first one. The second one is I want us to have f. We have this integration sign, and you have x cubed, and then you have minus 6x, and then you have 8dx. The third one is going to be, you have that, and then you have your 2x cube minus 6x, and then you have plus, you have 3 divided by x squared plus a 1, and then you have your dx. And then the fourth one, number 4, is going to be, I wanted to have this, and then I wanted to end up having a 2t squared plus t squared times square root t, and then minus 1 all over t squared, and then you have your dt. And then the fifth one, I want us to end up finding 1 plus cosine squared x divided by cosine squared x, and then I have a dx. And then the sixth one is saying we just wanted to find this one. We have t squared minus 1 divided by t raised to 4 minus a 1, and then I have a dt. I want us to solve each of these questions, or evaluate each of these indefinite integrals. There is no lower limit, and there's also no upper limit of integration. And if that is the case, then we are actually looking for the most general antiderivative, or the indefinite integral. So let's start with number 1, and we have our solutions there. This is not going to be hard at all. So our number 1 was, wanted to find this. We had 10x to the power 4, and then we have minus 2 sec squared x dx. So what is important here is very simple, that because I have two functions, I can always split these two and have 10x to the power 4 dx, and then have minus this one. I have a 2 sec squared x, and then I have a dx. The next thing is I can pull the constant out, so I have 10, and then I have x to the power 4 dx, and then I have a minus. I can pull out the 2 in front, and then I will have a sec squared x dx. And one thing for sure, if you go back to this integration table, you can see that whenever you have x raised to an exponent, just add a 1 and divide by that. And if you are having a sec squared, where is sec squared? Sec squared dx, that's just a tan x, so it's the same as a tan x. That is why you need to know this integration table by heart. So you'll have a 10 times x, I have a 4, I need to add a 1, and then I divide by 4 plus 1 and then minus, I have a 2, and then when it comes to this, I will end up the antiderivative, or particular antiderivative of this one is going to be a tan of x. Of course, I have to plus the constant of integration because I'm looking for the most general antiderivative. So I will have a 10 times x raised to 5, and then divided by 5 minus 2 tan of x plus a constant of integration. And then here you will end up having a 2x to the power 5 minus 2 tan x plus a c. That is what can be expected from number 1. Another thing, someone might say, because I splitted these two, I'm supposed to have a constant of integration for that and a constant of integration for that. Of course, if I have a constant plus another constant, I'm going to get a big constant. So it's not a big deal. You are not wrong. You are right. But it makes sense to have one constant of integration at the end if you are dealing with indefinite integrals. Let's go to number 2. Number 2, what was number 2? Wanted to have this, and then you have x cubed, and then you have minus 6x, and then you have a dx. This is the same as, I can just keep adding there. I have x raised to a 3, I have add a 1, divided by 3 plus 1, minus 6, I have x. Since there is a 1 there, I will have there's a 1, I have to add a 1 and divided by 1 plus 1 and then plus the constant of integration. Simply put, x raised to 4 divided by 4 minus 6 times x squared divided by 2 plus a c. Simply put, x raised to 4 divided by a 4 minus a 3x squared plus a c. That is what is important there with number 2. We have a 3, and then let's go to number 3. What is number 3 saying? With number 3, we want to solve. I have 2x cubed minus 6x plus 3 divided by x squared plus 1. This thing I have to have a dx there. So once you are having this, you will find out that I can deal with this one because I want to have 2x cubed dx minus this. I have 6x dx plus this. I have a 3 divided by x cubed plus 1 dx. The next thing here is this. Pull out the constant. I have x cubed dx minus 6. I pull out the constant. I have x dx. There is a 1 if there is nothing there. And then I have a plus. Pull out the constant. I have a 3. And then I have 1 divided by, this one was a squared, x squared plus 1 dx. So if you look carefully into this, you will find out that I will have a 2. And then when I'm dealing with this, I'll have x raised to 3 plus 1 over 3 plus 1. And then I have minus 6. And then I'll have x raised to 1 plus 1 divided by 1 plus 1. And then I'll have a 3 times, what is the antiderivative of 1 over x squared plus 1? That is actually the tan inverse of x plus the constant of integration. Again, if you are dealing with this, supposed to have a constant of integration. Dealing with this, we have another constant of integration. Dealing with this, we'll have another constant of integration. So we'll end up having c1 plus c2 plus c3. But adding constants, you will end up getting a constant. So that is why I have one big constant of integration. But if you are adding this by one, you are not wrong. You are 100% right. But you must know that constant plus constant plus constant will end up getting one big constant. And then you will have a 2, and then this one will be x raised to a 4 divided by a 4 minus a 6 times x squared divided by 2 plus 3 tan inverse of x plus a big C. And this is 2 divided by, how many 2's in 2? 1, 2's in 2, we have 2. So we'll have x raised to 4 over a 2. And then have minus 6 divided by 2, that's a 3x squared plus 3 tan inverse of x plus a C. That is what we're supposed to get here when it comes to number 3. Now we need to go to a number 4. What is number 4 saying? Number 4 we wanted to find, we have 2t squared plus t squared times root t minus 1 all over a t squared, and then we have a dt. So when you look into this, the best way is to make sure that it looks like some of the things that are actually in the integration table. We don't have a fraction here other than this fraction. I don't see any other fraction here. So let's first make sure it's only this one. Let's first make sure that we remove this fraction here so that it looks like something that we can deal with. So if you look into this, you will find out that we are going to end up having 2t squared divided by t squared plus t squared square root t divided by t squared minus 1 divided by t squared, and then you have a dt. And then when you are actually proceeding here, you will end up finding this t squared and this t squared will go away. You will have a 2 plus, And then when it comes to this, t squared and t squared will go away, and then you have root t minus 1 over t squared and then dt. So simplifying this actually makes our job easy, because this whole thing is the same as 2 plus t raised to 1 over 2 minus t raised to minus 2, and then you have a dt minus 2. It means that this whole thing was actually in the denominator. So when you're actually dealing with this, you will end up finding that you are having a 2. No, now it's time for me to actually solve it. The antiderivative of a constant, we know that is going to be a constant times the variable that is being used. So we'll end up having a t. That is what is important. When it comes to this, we'll end up having another way to look into this. If you don't like this, whenever you have t2 alone, you must know that we're dealing with t, so there is t raised to 0. So you end up having t 0 plus 1 divided by 0 plus 1. Of course, you get something nicer, but at the end of the day, you are just having 2t plus t 1 over 2 plus 1 divided by 1 over 2 plus 1, and then minus t raised to minus 2 plus 1 divided by minus 2 plus 1 plus the constant of integration. So once you are having that, you will actually find out that we are having 2t plus, and then you have a t raised to, if you look at 1, you must know that 1 is the same as 2 over 2. Why 2 over 2 is because I want to end up having the common denominator. And then the same thing here, 1 is the same as 2 over 2. Why 2 over 2? Because I want to have a common denominator. And then taking the common denominator, will have a 2. And then 1 plus 2, that's a 3, divided by, is the same thing here, 1 plus 2, that's a 3 over 2. And then here I still have a negative. I have t minus 2 plus 1, that's a minus 1. Minus 2 plus 1, that's a minus 1, and then plus a c. Of course, you can proceed to 2t, and then change this to multiplication. You will end up having a 2 times t raised to 3 over 2 all over a 3. And then minus and a minus is going to be a positive, t raised to minus 1 plus a c, or simply put, is going to be 2t plus 2t raised to 3 over 2 all over 3 plus 1 over t plus a c. That's one way to do this. Some other people, because we are having a square root in the given equation, they want you to have a square root if it's possible. So we'll end up having 2t plus 2, and then you have the cube, the square root of t to the power 3 over 3 plus 1 over t plus a constant of integration. Some people will actually want you to end up having that thing there. So if you are not having it like that, they would say that, let me deduct few marks, but I don't want you to lose any marks because the square root was there. Make sure you include it. Let's go to the fifth question. The fifth question was saying, I want us to find the indefinite integral of 1 plus cosine squared of x divided by cosine squared of x, and then you have a dx. So in most cases, you'll find out that it is easy to just first simplify and make these things looks a little bit easier. And this one is the same as 1 over cosine squared of x plus cosine squared of x divided by cosine squared of x dx. And then if you proceed normally here, you'll find out that you still have the elongated x, and then this one here, you know that 1 over cos is the same as secant, so this is supposed to be secant squared of x, and then you have cosine squared divided by x, and cosine squared x divided by cosine squared x, that's just a 1, of course, plus 1, and then you have a dx. Now, what is a particular antiderivative of sec squared x? You know that's just a tan of x, plus what is the particular antiderivative of a constant? Is that constant times this variable there, and then plus the constant of integration. And you'll find out that that's just easy as this. It's not hard. What is important? Simplify this to the fullest. And then let's go to the sixth one. The sixth one is saying find this antiderivative. We have t squared minus 1 divided by t to the power 4 minus 1 dt. Of course, this one also you can try and simplify and find out that you are having t squared minus 1 divided by t squared squared minus 1 squared, and you have a dt, a dt here. And now that you are having a dt, I want you to realize that you have a t squared minus 1. In the denominator there, this is a perfect square, so you will have a t squared minus 1 and a t squared plus a 1, and then you have a dt. Of course, t squared minus 1 and t squared minus 1, they cancel out, and now you are left with 1 over a t squared plus 1 dt. And of course, if you look carefully into this, that's just a tan inverse of this t plus a constant. I think that is actually going to be the final answer. You can see these questions are not that hard if you know this integration table. You want to make sure that you get this integration table to your heart and make sure that you understand each of these things, because the easiest way for this is to take the derivative of this and see if you are getting this thing that is inside. That's all there is. And make sure that you understand these things. We did these derivatives one by one. Now it's time for us to undo them. So that is what is important here. Of course, I am going to end here. So I will end here when it comes to this one. And then the next thing that I would want us to ask ourselves, how would we find the most general antiderivative of this function 2x times, let's say we have x squared plus 1. How would you end up evaluating this? Because now you have a multiplication of two functions, but there's also a relationship between this function and that function. So how do you end up finding the antiderivative of this particular function? Of course, the answer to that is actually the substitution rule, which is known the U substitution. Others call it that, but let's just stop there and see. Maybe you can try and see if you can make use of the examples that I've given you and also the table here. If you can use that, then I will be happy for you, because it means that you are ready for the exam or the test. So we're gonna stop there for now, and then in our next lesson we'll look at the substitution rule and how to apply it. Hopefully you will understand it more than you already are.